happens at position number 2. Position number 1 is the 0 frequency. Remember, MATLAB indexing starts with 0. These are all discrete numbers. Okay, if I use 10, then it's clearer that this is just one peak, right? One peak has 2. The rest all 0, right? Can see that? Okay. So in this case, this is position 1 is 0 hertz, and position 2 happen to represent 1 hertz, right? Right. But if I change my sampling interval, right? Say 0.0. 40 milliseconds. And I sample for say 3 seconds, right? How many hertz this represents? Now you like anything that A is the frequency set, right? Right? Is the N is the frequency domain, right? Right? But if you want to change it to hertz, then you have to tell me what was your sampling frequency. Got it? So for this lecture, we are going to see how we can establish what's the sampling frequency. I'll let you scan the QR code later. Okay, so it's the subject of the first half of today's lecture. The subject called frequency resolution. It's for you to answer that question just now, right? When you're given the FFT, instead of K, you want to change the horizontal axis to hertz. How are you going to change it? Okay, so you need to know every unit of K represents how many hertz. Okay, so frequency resolution, if you go through we'll go through some derivation. Okay, so you learn about DFT, right? And which was implemented using FFT, right? Now, this set of slides is about interpreting the results of FFT, meaning FFT result gives you horizontal axis in small k, right? Indexed by k. You want to change the axis to hertz. Okay, how to do that? When you input a vector of say 8 numbers into an FFT function, and you get an output vector of length 8. How do you interpret the output vector? Okay, so you want to ask how many hertz. Okay, again, when you have an input vector here and the output of FFT, the first position is always representing 0 hertz. Understand? 0 hertz, and this is positive frequency, and from here, this direction is negative frequency. Okay. Okay. In fact, if this is negative, if this is a frequency F1, for example, represent F1. This one will be minus F1. Understand? If this is F2, this will be minus F2. So it goes this way, and here minus goes this way. Understand? Okay. So this is how FFT this is what you get from FFT result. Now, you almost always want to give even number for FFT. Okay, in fact, you give a power of 2, but we'll do that later. But if it's an even number and the first number is already taken out by 0, right? So surely there must be an unequal number of positive frequency and negative frequency, right? Right? So FFT result will always give you a 0 and positive frequencies here and negative frequencies here. And the negative frequencies will have one more element than the positive frequency, because positive frequency donated one item to represent 0 frequency, understand? So if this is 0, F1 hertz, f2 hertz, f3 hertz. This will be minus f4 hertz, minus f3, minus f2, minus f1. Understand? Okay, you may want to write it down. You may want to write it down this way. Let's say. Probably there's a slide that writes this later. It's okay. Never mind. 0 hertz, right? Minus f1. Sorry, f1. F1. F2, F3, and then you have minus F4, minus F3, minus F2, minus F1, okay? Okay? Oh, right? So this is what you get. All right? Okay, so my negative frequency, we always have one item more than a positive frequency. Alright? But usually when you do FFT, you have thousands of items, right? There's no difference. 1 million is equal to 1,000,001, understand? As far as this course is concerned. So usually when you do this kind of thing, you must know when to throw away insignificant things. Okay? Now, to answer the question how many hertz, we need to understand the concept of frequency resolution. So to understand that, right, let's look at the continuous Fourier transform first, right? From continuous Fourier transform, we know that we know that you can actually discretize them, right? Discretize them because remember just now the illustration, I illustrated to you that by changing the sampling frequency and changing the number of points of the array that you put in for FFT, you get a different way to interpret your frequency axis, right? Right? So you need to start from continuous time Fourier transform first, right? Then you start to discretize, then you see the relationship. So if you look at here, right, this is a continuous Fourier transform, right? Continuous Fourier transform. By now, you should be able to write this equation. If you are sound asleep and I suddenly wake you up and ask you what is the formula for Fourier transform, you will tell me, understand? Right, but if you cannot remember this, it just means that you didn't stare at the slide long enough, right? But final exam is open book, right? So if you don't feel like memorizing this is perfectly alright, right? But sometimes you see long enough, you can remember. Okay. Now, if you do a Fourier transform and then you use a Fourier transform equation for continuous Fourier transform, right? Now let's try to discretize things. Okay. When you have a delta t here, I change it to delta t here. Okay? And then f, so the t here, right? I discretize the time. Can the people at the back see this clearly? Can you see the small ft and the big T here and delta t here? You can, right? Okay. So t time is equal to n times delta t steps, right? Because in the time domain, you already discretize into index n, right? And then h of curly bracket t becomes h of square bracket n, right? Because now we are talking about discrete axis, now time axis. So from here to here, right? And then when you integrate from minus infinity to plus infinity, right? Here by right is also minus infinity plus infinity, right? But just take it that the n is very big here, right? N is very big here, right? It's like infinity here, right? So the two are equivalent. So you can take out the delta t here, and you're left with what is inside here, right? Because this summation is with respect to n. T is a illustration just now I used 1 millisecond, 14 millisecond, 15 millisecond, right? Right? Okay? Now, sampling interval, 1 millisecond, what is the sampling frequency? What's the sampling frequency if the sampling interval is 1 millisecond? What's the sampling frequency if the sampling interval is 1 millisecond? 1000 hertz, right? Is 1 over the sampling interval, isn't it? Okay? So, is 1 over f of s, understand? Okay? 1 over s. F of s is sampling frequency. Now, so delta t is replaced by 1 over fs. Okay? It's replaced by 1 over fs. So now, if you look at it, so I just copy the same equation just now here, right? So just now we discretized the time axis, right? But now we are going to discretize the frequency axis also. Okay? Now, so to discretize the frequency axis, I'm going to write f in terms of k times delta f. Delta f is the frequency step on the frequency axis, understand? Which is the frequency resolution we are talking about. Every step in the output of FFT, every step represents how many hertz, right? So k times delta f, okay? And so f is replaced by k times delta f, okay? Now, listen. When we did discrete Fourier transform earlier, right? And discrete Fourier transform actually gave us this equation, right? This is one equation that you must know very well also, right? E to the minus j2 pi k n over n. Okay, n is the total number of points that you use for the FFT, right? Input, output, same number of points, capital N. Okay, so if you compare the two, ignoring the scale factor, ignore the scale factor. Why ignore the scale factor? Because loudness does not matter, right? Loudness does not matter. Huh? Scale factor is about loudness, the volume, okay? Does not matter, so just ignore them. Just compare what is inside here. If you compare what's inside here, this must be equal to this, right? And then you end up with this expression here. Delta f divided by fs is equal to 1 over n. Alright? I give you like 10 seconds to by the way, how many of you here are not a student of this class? How many of you are not a student of this class? Okay, so you have this expression, which means that the frequency resolution is equal to sampling frequency divided by number of points that you use for your FFT. Okay, so this is a very important expression. Okay, this expression allows you to interpret your FFT output, right? Because the FFT output is nothing more than an array of numbers, right? And the index is small k, right? Frequency step, right? If you want to attach how many hertz to it, you need to know what each gap represents, how many hertz each step represents, right? And that step is given by FSOM. Sampling frequency divided by number of unit points. Now, in subsequent tutorial, right, and also I can do that as a use of ask you all to do some work on that. Have you all learned how to whistle? Good. Try to learn how to whistle, okay? Right? If you whistle, it makes if everybody can whistle, or you can get a friend who can whistle for you. The project can be fun and the project is manageable. Understand? The reason is very simple. When we speak, right? When we speak, our voice comprises many different types of frequencies, very complicated. Music or sine waves and cosine waves, understand? Whistle is very sinusoidal. That makes frequency analysis easier, understand? Okay, so learn how to whistle. In the tutorial, I don't expect you to whistle yet, but we can download those kind of, those kind of, when you play when you play a guitar, for example, you have a good tuner, right? The tuning fork and all that, they give you very pure sinusoidal tone, right? We can use that as input, but if you can whistle, your project will be more fun. Okay? Now, so remember, this expression, this is a very important expression that allows you to interpret how many hertz is your output of your, your FFT result, right? How many hertz is, you see this peak here at position number 10, for example, how many hertz does it represent? You use this formula, you multiply the 10 by the delta 10, and you get the hertz. So it's sampling frequency divided the number of times, the number of points you use for your FFT. Okay? So, so input is here, FFT output is here, zero frequency is here, then you have delta F, 2 delta F, 3 delta F, minus 4, minus 3, minus 2, minus 1. Okay? Okay? Now, sometimes for visualization only, right? For visualization, you don't like to see this kind of thing very awkward, right? Right? So you do FFT shift. So this is what happened. This is what happened. Remember, when you do DFT, everything is periodic, right? Yeah? Everything is periodic. So when you have, let's say, a sine wave here, when you have a sine wave here, right? And then you plot your FFT, you get a peak here, right? This is 0. And then you get a peak here, right? And from here to here is positive frequency, right? From here to here is negative frequency, right? Right? But remember, when you do FFT, everything is periodic, right? So this whole thing here repeats here, I understand? The whole thing here. Let's say this is A, this is B, right? The A will repeat here again, and the B will repeat here again, understand? Understand? Same thing here on this side. The B will be here, and then the A will be here, understand? Understand? It keep on repeating, right? So the FFT result will show you this interval, right? But what human likes to see is actually this interval, isn't it? With 0 in the middle, right? Yeah? We like to see 0 in the middle and then positive one side and negative one side, right? Yeah? So there is a function. In MATLAB, there is a function FFT shift. I think if you do Python, there is no such function, if I'm not, I may be wrong, but suffice to say that almost all computer languages will give you FFT package because it's so useful. But not everyone will give you the FFT shift, understand? For visualization, okay? Now, so if there's no FFT shift, for you it's just simple, right? Just copy one side and put it the other side, right? Yeah? Right? So you understand why FFT shift bring the 0 to the middle, because it is periodic. So you just shift the window only, right? Right? So you get one side positive, one side negative, and 0 is in the middle, and then human will be happy to see that because then you feel more balanced, right? Right? You feel more balanced, more intuitive, right? So it's 0 and then positive and then negative this way, right? And it's not like, you have 1, 2, 3, and all of a sudden becomes -1, -3, that kind of thing. It's very confusing. Any questions so far? Okay, so this is how you interpret your FFT results. Okay? So after FFT shift, you have delta F minus delta f. 0 is here. After FFT shift, you have 0 here, delta f minus delta f, 2 delta f minus 2 delta f, 3 delta f minus 3 delta f, and there's a lone minus 4 delta f here. Okay, which you can ignore, right? Right? Now there's one thing that when the signal is real, when the input signal is real, right, the FFT magnitude always gives you one symmetrical result, right? Right? We went through this, right? Right? When the input signal is real, the FFT result, the magnitude is always symmetrical. One side is A plus JB, the other side is A minus JB. Right? We did this last week. We did this last week, right? Where is it? Yeah, here. Right? If x is real, then you have this relationship, right? So even though the minus delta 4 delta f frequency is there, positive 4 delta frequency is not there, right? In the FFT result, right? So even though minus 4 delta f is here, there's no 4 delta f, right? Right? But if I tell you that the input is real numbers, it's all real numbers, can you infer what is 4 delta f? Yes or no? Yes, right? It's just a complex conjugate. Understand? Okay? So that's how you interpret the FFT. Now, so let's see some examples. This is a 50 Hertz sine wave, and then sine wave stored in an array is this, right? We did this just now, right? In my MATLAB example, right? And then the frequency spectrum of the 50 Hertz sine wave is here, right? Frequency spectrum of sine wave stored in an array. This is after FFT shift, understand? So this is 0 Hertz, positive frequency, negative frequency, and then here is at 50 Hertz. Okay? And the array returned by FFT function call before your FFT shift is actually this 0 Hertz, positive frequency, negative frequency. Alright? So it should be very clear now how to interpret FFT result. And this is very important. If you don't know how to interpret this, then you'll be in trouble, right? Right? Now, I'll give you some supplementary materials, right? And this is something we did last time also, but I just want to reinforce it again. Periodic in one domain leads to discretize axis in the other domain, or the other way around. You discretize one axis, the other domain becomes periodic, right? Yeah. So when you plot, cosine. So what is the FFT of a cosine? Is it real number or imaginary number? Real or imaginary or complex? Real. How many say real? How many say imaginary? How many say complex? All of you are going to fail the course. How many say real? How many say imaginary? How many say is a complex number? So it's real number, understand? It's real number, and this is one JPEG, discrete cosine transform capitalized on. Okay? We'll do that next time. So this cosine, when you do FFT cosine is real number, right? So you have positive f and negative f here, right? And this is in the continuous time world, there's no periodic, understand? In continuous time world, there's only two peaks, they don't repeat itself, understand? And then when you have two cosine waves together, right? Two cosine waves together, you add up, you have two cosine, right? And so two frequencies. One is F naught, one is KF naught. Okay, one is F naught, one is KF naught. Now, I didn't explain well, I think. So we all know that sine waves and cosine waves are continuous time, right? Right? And sine wave, cosine wave only give you one frequency, one and only one frequency, right? Positive, negative, right? So whether you're using a continuous axis or a discrete axis, there's only one peak, right? Right? There's only one peak, right? So the rest of the positions are all zero, right? So if you have a cosine wave, right, and then the frequency of cosine wave is F naught. Let's say the fundamental is F naught, right? And I'm going to add cosine of multiples of this F naught, right? Right? So when you do FFT, remember FFT is a linear operation, meaning when you have two input add up together, the FFT result is simply the FFT of this plus the FFT of this, understand? Okay? So it means that you can just superimpose the two results here. Right? This one gives you here, this one gives you this peak and this peak, right? Right? Now, when the signal is periodic, only discrete frequencies are present, right? Whether when you have a sine wave, cosine wave, there's only one frequency, right? These discrete frequencies are multiples of F naught, where F naught is a fundamental frequency. Recall that the period of a composite signal is given by 1 over F naught, right? Right? 1 over F naught is the period of the signal. Therefore, when the period of a composite signal is large, listen, when the composite signal, the period is very large, right? Your F naught becomes very small, right? Because it's 1 over F naught. Right? So all the discrete frequencies representing the signal are very close to each other, right? Yeah? In the extreme case, when t approaches infinity, that means the period is infinity, right? F naught becomes extremely small, close to zero, right? So the signal is practically non-periodic. And when t approaches infinity, the signal is practically non-periodic, right? So F naught will approach zero. In this case, the frequency axis becomes continuous. Understand? So you can move from continuous to non-continuous by having this reasoning. Understand? Okay? Okay? When you have a sine wave or a cosine wave, you have a small interval of periodic, right? The period is small, right? Right? So when the period is small, 1 over small number is a big number, right? So your frequency is large, right? 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 Now when you have when the period is infinity, right? Right? Then the frequency, the very basic frequency that you can represent F naught is close to zero, right? Right? And you know that for all the frequencies, all the signals that we are talking about is the multiple of this basic F naught, right? I think, okay, listen. In the tutorial, you also see what is the fundamental frequency, right? If I give you a set of frequency, what is the fundamental frequency, right? Right? And the fundamental frequency is the basic unit in which all the other frequencies can be represented by using this and multiply by integer numbers, right? 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 So this fundamental frequency is the F naught that we're talking about, understand? Okay? Now when the F naught is very big, right? When the F naught is very, very small, which means that the period is very big, then you can represent practically all the frequencies on the axis, understand? Because F naught is very small. It becomes continuous. I have a feeling I didn't explain well. Who think I'm confusing? Oh, okay. Right? Okay? So actually the two cases, the continuous axis and discrete axis, actually they are linked together. Conceptually, you just do the extrapolation. Okay? Now, this is the end of this set of slides. Let's take a break and not take a break now, but scan your attendance. Yes.
So you said that as the period becomes infinity, the fundamental frequency tends to zero.
Yes.
So then, in real life, like most signals are non-periodic, right?
Yes.
So then, what do you use the fundamental?
So the fundamental frequency tends to zero. It means that it is like every frequency is representable, right? It's so small that the curve becomes continuous. So what it means is in real life, when signals are not periodic in general, right? Every frequency is possible. That's what it means.
So our fundamental frequency will be 0.000 something.
Yeah. It is like almost zero kind of thing, right? So every frequency is representable, right? But the moment you go and use FFT and you can discretize everything, then certain frequencies are not representable now. Make sense? Yeah, those of you who cannot log in your QR code, you just drop me an email that that the QR code doesn't work. Now, some of you wrote to me, you have some valid reasons you can't attend. It's fine, understand? Okay. I have this system here because the school implemented this, and so I just use it, and it's useful for me to keep track of whether there are students who are perpetually absent from the class. Right? I got a name list and things like that, and I want to arrest the problem earlier, right? And also if you run into any trouble later, right? And then you come and tell me special consideration or whatever, then I look at your attendance, you never attend classes, how I'm going to help you, right? Okay, so I'm not going to use this to affect your grade, understand? Your grade won't be affected by the attendance, but then use it for some other purposes, right? Okay, but if you cannot attend lecture, just drop me an email, right? With the reason, it's fine, okay? But try to come to the lecture. I use a lot of illustration and things like that, so there's no way I can deliver effectively if I record and things like that. So I'm not going to record and go on to webcast also. Okay? And also, more importantly, when I teach, I want to see your expression. Then, your facial expression means a lot to me, understand? If you understand, I can see you understand. If you don't understand, then I want to repeat, okay? So I don't want to teach to a class. During COVID time, when we had to do Zoom, it was ineffective and not effective at all. I don't even know who I was teaching, understand? And I don't know whether students understand or not, because I can't see their face. Okay, so that was the reason I want physical class. So the next topic that we are going to do is a topic that is very interesting, and it's also very important. It's a topic called convolution. Right? Now, this word was a very strange word to many people before deep learning. But it exists in the signal processing world for a long, long time. Okay? And then somebody used the concept of this convolution into neural net deep learning. Right? In fact, it wasn't deep at that time. The person who did it, who used this concept to apply to neural network, was a person called Yann LeCun. He was one of the 3 persons who won the Turing Award like a few years ago. Right? He did this, in fact, before the deep learning era. That was in the 90s. Right? He designed a neural network using convolution concept to recognize handwritten characters. Okay, at that time you don't have deep learning, the computer wasn't as good. Okay? But it was successful as a handwritten character thing. And then it becomes convolution neural network, CNN. A lot of you heard about it, right? Right? Now, those of you who learn CNN from neural network, I want you to flush away your knowledge there, understand? Because the person who did the Yann LeCun, who did the convolution neural network, he used the gist of convolution to implement his neural network, but it's not the full version of convolution, understand? It's not the full version of convolution, okay? So for signal processing purposes, you have to use the full version of convolution, understand? And this is the concept that you want to learn today. All right? Now listen. A thought experiment, huh? I give you a thought experiment. Okay? I have a bell here. Huh? And every time I hit the bell, I knock the bell, right? The bell will give me this sound. This is time axis, right? The bell will give me this sound. 5, 4, 3, 2. Ding! Disappear, understand? Ding! Disappear. Okay, I'm using the discrete version. Of course, the real one is continuous, right? I'm using the discrete version. Ding! Die, right? Ding! Die. It lasts for a few seconds and then it die, right? Right? And then it gets softer and softer, right? Okay? Now, if I hit this bell at different time intervals, I hit it, right? Then at time 0, when I hit it, it gives out the thing, right? Right? Now, this bell has got a property called time invariant. That means today you hit it, it give you this. Tomorrow you hit it, it also give you the same pattern, understand? It's time invariant. It doesn't matter when you hit it, it will give you the same output, okay? So that is called time invariant, understand? Okay? The other thing that we want to assume is, you know, when you hit the bell, the air vibrates, and that's how you hear it, right? Right? Now, when you add up 2 bells, right? What you hear will be just the addition, understand? There's no saturation or nothing, okay? Okay? We're going to assume it is linear in that sense, right? Linear in the sense that if you hit the sound you hear, and then you hit another sound, and that you overlap with it, the resultant is just the addition, understand? Okay? So this is what we call a linear time invariant system, understand? It's linear and it's time invariant. No matter when you hit it, the bell is the same, understand? Okay? Now, so we go through some thought experiment. If I have this bell, right? Now this is so my time axis is here. This is my time axis. before this thing dies, I'll hear this, right? Yes or no? Right? Okay? And then at this time set number 3, I also hit another one, then I'll hear this. They are all the same, huh? Right? Yeah? And what do I hit? And so this is time invariant. Okay? This is time invariant. Okay? And the resultant of what you hear is an addition of all these, right? Right? You just add them up, right? And this is called linear. Okay? It's a linear time invariant system, okay? Okay? Now, there are a few concepts or a few terminologies here that you need to be aware of. Huh? When you hit the bell, and the bell gives you this sound, right? When you hit the bell, you're giving it an impulse, right? Right? You punch it. It's an impulse, understand? So this thing is known as the impulse response. Understand? Impulse is known as the impulse response. You hit the bell, you hit the bell, the action of hitting the bell is an impulse. Right? And what the bell responds, right? What the sound that the bell gives you is the impulse response, okay? So you have impulse, you have impulse response. Okay? And then you have the time invariant system because the impulse response is always the same no matter when you hit it, right? Right? And the result is the addition of all the hittings, right? All the sounds that you hear, and that's linear. Okay? Okay? Right? So linear time invariant system, that's what it means. Another thing about linearity is this. This is assuming I hit it with the same strength, right? If I punch it with double the strength, then the output will be double, understand? Okay? Okay? So this is another property of the linearity, understand? Okay? Okay, so this is linear time invariant system. Now, why is linear time invariant system so important? It is so important because it's extremely useful. It's extremely useful, huh? Now listen, huh? If you have a question, you say, I have this bell here, right? Same bell, right? Same bell. And I hit it with different strength. This is time axis. I hit it with different strength, for example, right? At different time interval, right? I hit different strength, sometimes harder, sometimes weaker, right? And I ask you, what will I hear? Listen, if my input is like I tell you I hit it with different strength, right? Different strength in this sequence. What will you hear? And your answer is as long as you tell me what is the impulse response of this system, as long as you tell me these things, I can answer your question. Understand? I repeat. If someone says, I take the bell and I hit it in this pattern with different strength, right? What will you hear? And your answer will be, as long as you tell me the impulse response, I can give you the answer. Okay? That's how powerful impulse response is. Understand? For this reason, I think in the engineering world, sometimes we call it system identification, whatever. Right? You give me a black box, you don't know what is it. As long as you tell me if I have an impulse, the output is something. Right? You give an impulse, output is something, I know everything about the system. Understand? Right? Is that powerful? Huh? Right? So it's like you tell me I hit the bell and then this is what I hear. I know everything about the bell. Now when process called convolution. It's about 11 o'clock now. We take a break. We come back 5 minutes later, and then we come back 5 minutes later, all right? So we take a break now. Discussing, okay, since some of you are still not here yet, I can have a small talk with you. Because our tutorial is always due on Monday, right? Right? And Monday is a public holiday, right? Right? So I asked my friends, will it be alright if the tutorial submission, the deadline is on a public holiday on the third day of the Lunar New Year? All my friends scolded me, understand? They say, this is the kind of professor that we always scold you, Now listen, I'm still going to put Monday as the deadline. But if you need extension, just write to me. Extension of 1 day, just write to me. No penalty, understand? Because I don't want to change this just because it's a Lunar New Year. What happens if next time you have the Indian holiday and then the Malay or Muslim holiday? Then we have to change and everybody will be confused, understand? We rather keep to the same Monday deadline, understand? But in future, if it is an Indian holiday or is a Malay or Muslim holiday, you just write to me if you need extension, understand? Or any other ethnic group that's a special day for you, understand? Alright, so I'll still put Monday, but don't scold me, understand? If you need 1 day extension, just write to me. Alright? So, once again, Happy New Year, Happy Holidays. So, convolution. Now, convolution is used for various purposes. Example, to explain what you hear when you hit the gong, right? Hit the bell, multiple times, right? That's one-dimensional convolution. You can do convolution for images also, understand? When you take a picture and the picture got blurred, right? Because you didn't focus properly, and the picture is blurred, that can be explained using convolution also, right? It's a very, very useful tool. And then it's so useful that it's also used in neural net or the CNN, right? Right? So this is an illustration of what we just did just now on paper, right? So you have a gong, right? Right. And then you have the impulse response of the gong. So in order to study the system is the gong, right? To identify the system, right? What you need to do is you can hit the gong one time. Then you record what is the response, understand? The moment of the action of hitting the gong is impulse. The response of the gong, the sound that you hear is impulse response, understand? Impulse response. Okay, impulse response. So the sound of gong can last for a few time sets through go weaker and weaker through time. You hit it at T0, then it goes down, right? Yeah? Now, this one can be a bit confusing. Let me go back to the visualizer again. Now listen. What we're going to do now is to answer the question just now. If I hit the gong at different strength, different time, what would you hear, right? And then we know that as long as you tell me the impulse response of the gong, I can tell you what we'll be hearing. Okay? Now, if you hit, let's say this is the hitting pattern, right? For the time being, I just assume you hit with equal strength first. You hit with equal strength, right? This is a hitting pattern, right? Right? This is when you hit the gong, right? This will be what you hear. This is what you hear. Right? And then hit it here, and okay, I hit another one here. You hit here, right? If you sorry, right here. Assume this is a line. This is a line, okay? Then you hit it here, you get this, right? Right? And then this one, you hit it here, you get another one, okay? Now, if I ask a question, right? If you put your ear at this point here, if your ear is here, this is your ear. I don't know how to draw a ear. Ear is like that, right? You ask me what will you be hearing, right? Right? At this point in time, right? If you, okay, I draw the impulse response here, right? Right? If you say you put your ear here at this point in time, you ask yourself, what will you hear when the hitting pattern was like that, right? Am I right to say, listen, very crucial point, am I right to say that you hear the sound from this hitting pattern at this strength, and you hear the sound of this pattern at this strength, right? Yeah, because it gets weaker and weaker, right? And the sound from this pattern is even weaker, right? The sound from this pattern is even weaker, right? 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 So am I right to say that if you put your ear here, you'll be hitting a pattern, or you'll be hearing this much of this hitting, right? And this much of this hitting, and this much of this hitting, and this much of this hitting. Correct or not? True or not? Yes? Yes, right? Right? And then because it's linear, you just sum them up, right? Right? Yeah? So in other words, if I give you a pattern, hitting pattern like that, it doesn't need to be the same strength, it can be any different strength, the hitting pattern, right? Right? All you need to do is, you say if your ear is here, right? Your ear is here. I can't even draw a ear. Ear maybe is like that, yeah. Your ear is here, right? You're going to get this much of this pattern, this hitting strength, and this much of this hitting strength, and this much of this hitting strength, and this much of this hitting strength, right? You got to multiply them and sum them up, right? Yes or no? Yes or no? So in other words, if you want to answer the question, okay, at this point in time, what will I hear? What do? You take your impulse response and you flip them, right? Yeah? You take your impulse response and you flip them left and right, and then you can multiply, right? Yes or no? Right? So you take, so you have this hitting pattern, and then what you need to do is you take this, the impulse response is like that, right? Right? You flip this impulse, you flip this impulse response left and right, and then you multiply them and sum them up, right? That will be what you hear, right? Understand or not? So that will answer the question. Now, if you tell me, what about at this point in time? What do you hear? Same thing. You take this pattern and multiply. So this one doesn't matter now. You multiply like that, right? Yeah. Yes or no? Okay. Right. So at any point in time, I can give you the answer. I can give you the answer at along the t-axis, time axis. I can tell you at any point in time what you'll be hearing. Understand? I only need to know one thing: your impulse response for me, and your input, how you hit it. I can tell you what you hear. How powerful is that, right? It's a very powerful tool, right? And for that reason, when you know the impulse response of the gong of the system, you know everything about the system. Yes?
we assuming that if you hit it, it doesn't take longer to decay, right?
What's your
If you said that normally the impulse response is 4 time units, right? Until
Yeah.
it goes to 0. But if you hit it harder, it won't take longer.
it will take longer. The shape is the same.
Is that our assumption?
It's only up and down only. Right? That means that's a very good question. Huh? What's your name? Sorry?
Fahim.
Fahim, right?
Yeah.
Fahim asked a very good question. He said that because this is counterintuitive, right? Yeah. Because he said that if you have a gong with the input pattern like that, right? Right? The impulse response like that. Then he said if you hit harder, will you get more sound here? Right? Because this is like intuitively it should be so, right? But no. You don't get it, understand? You don't get any more sound. If you hit harder, you only get multiple of this. What was 0 is still 0, understand? Right?
The paper is obvious.
Thank you. Right? So it is like that. And if you hit harder, you get harder only. Right? If it's 0 here, it's still 0. You won't get any more. You won't get new response that come on. Understand? But he asked a very good question, and that was intuitive. I like you all to think intuitively what Fahim did. Understand? Intuitively, I think you should, right? But no. Like in doing this kind of impulse response kind of thing, you don't have any more new response. You only scale it according to how hard you hit. Understand? So that's a very important point. That's why it is linear time invariant, and then it's linear and things like that. It doesn't produce any more new result. It's linear, okay? Any other question? If not, we go back to I don't know when I can take off this thing. It's week 4 already. So you hit at time 0 here, time t0 here, and if you here at time t0 here, it's going to be a flip version of the impulse response, right? This is what I just explained, right? If you look at the slide. Okay. So in other words, okay, this process of flipping, multiply, and sum. Then for this time step, flipping, multiply, and sum, this process is known as convolution. Understand? This is the convolution. When you do CNN and all that, the neural net and all that, there's no flipping, right? Right? And then worse still, they say you don't need to do it at every time step. You can have a strike or something. You can jump step. That's not allowed in signal processing. Understand? Okay, for real convolution, you flip it and then you have to do it every time step. Alright? So I give some numbers here, right? You hit this is I hit at time 0, and then this is the impulse response, right? And then so this is one example, right, of going through an example of going through the convolution process. Okay, so you have the impulse of the gong, right? Right, impulse of the gong. So the first thing you do is you flip this impulse response, right? This impulse response of the gong. You flip this left, right, flip right. Laterally, you flip them. And the strength of hitting the gong at different time steps, it can be any pattern, right? Right? What will you hear? You ask a question, what will you hear, right? So the first thing you do is you flip it and then you say, what do we hear at time step 0? So you time step 0 and then you put it here, right? Right? So at time step 0, of course, you hear 5 times 3 and nothing else, right? Yeah? So you got 15. Right? And then you say time step 1. And time step 1, what will you hear? Of course, you hear the 5 times the 2 here, plus the 4 times the 3, right? Yeah? So this is what happened, 5 times 2 plus 4 times 3. And what is that? 22. Right? And then at times that 2, what will you hear? You move here, and then it's 5 times 4 plus 4 times 2 plus 3 times 3. And that will give you 37. Understand? So it's a process of sliding through. Understand? You use an impulse response to slide through your input and multiply and sum at every step. Okay? And then at this point, at time step 3, that is 5 times 3 plus 4 times 4 plus 3 times 2 plus 2 times 3, right? Yeah? You get 43. And then 5 times 1 plus 4 times 3 plus 3 times 4 plus 2 times 2 plus 1 times 3. Yeah? And 36. Okay? Now is that all? Is that all that you hear? Is that all that you hear? No, right? Because you still hear the remaining sound from the most recent hit, right? Right? So to know the time step number 5, what you hear, you similarly you shift up again, understand? And becomes 5 times 0, 4 times 1, 3 plus 3, 3 times 3, 2 times 4, you add them up, understand? Then it's 23. So on and so forth, understand? Until, and you get what I mean, until you shift up completely and then it dies off. Is that clear? Okay? So in other words, just by assuming the system is linear time invariant, no matter how you hit the bell, I can tell you what you'll be hearing. Okay? So that's what convolution gives us. That's why convolution is a very important concept, right? Now, convolution is a process of sliding a window. Convolution, there are various names, there are some terms here, and you know the impulse response, right? Impulse response, sometimes people call it a kernel, sometimes people call it a filter, understand? Right? Okay, so doesn't matter. Just keep it that way, and I mean, just understand. Just understand the process is more important than the term. In fact, you have impulse response for images also, and in images you don't call it, you call it point spread function, understand? That means if I have a light source, a very sharp light source, and you take a camera, take the light source, you don't get a very sharp point, right? You get a blurred point, right? And that's the impulse response, understand? Of the camera. Okay, of the imaging condition, the impulse response. And the impulse response in the imagery domain, you call it point spread function, right? Point spread function. The same thing. No. Convolution is a process of sliding a window over the signal and replacing each point in the signal with a weighted sum of its neighbors. We did it just now, right? So the kernel or the filter or the impulse response defines the weights. So next few slides, we will assume a signal X convolving in kernel given by H, and you can think of X as a hitting pattern, and H the sound created by each hit. Meaning X is a hit pattern, right? And then H is the impulse response of the bell or the gong. Right? So this is just some example. Right? Now, if the signal, the hitting pattern is a flat thing, and H, we usually represent impulse response using the small h. The small h here, right, is an impulse response. So the very first thing you need to do is to flip the h to become here, right? Flip with respect to 0, right? Yeah? Flip and get this, and then you start to slide, right? So after flipping, right, you can forget about this row. Huh? You just this one, this, multiplied by this, will give you this, right? Right? Then the next step you slide it, so you slide towards the right, right? Then it will be this multiplied by this plus this multiplied by this will give you here, right? Yeah? And then you slide again, this multiplied by this, plus this multiplied by this, plus this multiplied by this, you get you this. Right? And then you slide again, same thing. These three multiply, sum them out, give you this, and slide again, right? And the interesting part here is you start to slide out already, yeah? You slide here, this multiplied by 0 plus this multiplied by this multiplied by this, you get lower value now, right? Right? And then you slide, go even lower value, and then when this completely slides out, is 0 times 0 is all 0, understand? Okay? So when you have two when you have two kind of this kind of rectangular function conform with each other, you get slanted edges at the side. Okay? You get slanted edges at the side. That's what the result tells you. Okay? So that's one example of the convolution. Now, what we have been doing so far is something called linear convolution, right? It's very intuitive, right? Linear convolution is what happened in real life, right? Right? Now, I'm jumping the gun now. The convolution is so nice, and we use it most all the time, is because when you do this multiply and sum, multiply and sum, multiply and sum, it's a very tedious process, right? It's a very tedious process. It consumes a lot of computation power. It's very slow, right? Right? In real life, we don't do it this way, understand? When you do the implementation, we do it through Fourier transform. Because in the FFT world, it is extremely easy to do this kind of, you don't need to do multiply and sum. Multiply and sum, you don't need to do this, you don't need to slide a window and things like that. In the FFT world, we'll do later. You see that actually it's just some FFT. Okay, I give you some I give you some idea of what's to come next, huh? Okay. So what we have done so far is a linear convolution, which is what happened in real life. Okay. Now, so you have x, right? X is the heating pattern, right? The heating pattern. Right? H is the impulse response, right? 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 And then to get what you hear is y, right? Y is actually x convolved with h, right? Yeah? This is a symbol for convolution. Right? Right? You have an x and then h, then you multiply and sum, you get a y, right? Y is what you hear, right? Okay? And the process is very tedious. Multiply and sum, multiply and sum, multiply and sum. It's a very slow process, understand? It's a very slow process, huh? And all these are time domain, and time domain, huh? Okay? Now, in practice, when you do your computing, you don't do it this way. It's very slow. Right? Your for loop and all that is very slow. Right? What we'll do next is you'll see that if you do an FFT of y, you get y of, you get y FFT, right? You get y of k, FFT of k, right? Right? FFT of n, h, you know, it's discretized already, not continuous anymore, right? And FFT of x of n to give you x k, right? Right? FFT of h of n to give you h of k, right? 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 The multiply and sum can be done with just one statement in your program, understand? You don't need to write a lot of for loop and very slow, understand? Okay? Y of k is equal to x of k multiplied by h of k, understand? We will see this later. I mean, you don't have to understand, but this is the result that we'll see later, understand? So So when you do FFT, you multiply two FFT together in the time domain is doing the convolution. We will see this later. I don't expect you to understand now. I'm just giving you some idea of what's to come, understand? Okay? And so instead of doing multiply and sum, your y of n is equal to inverse FFT of y of k, right? And it's equal to inverse FFT of x of k multiplied by h of k, right? Right? So in MATLAB, your y of n is y, your y is equal to IFFT x, your FFT of x dot star FFT of h. Understand? Okay? In MATLAB, by now you should know, right? MATLAB, when you do a multiply, it's a matrix multiplication or vector multiplication. If it is a point-wise multiplication, it's dot star, understand? That means it's dot star. That means if you have a two vector 1, 2, and 3, 4, right? This is A, this is D, right? In MATLAB, A transpose is this, right? Yeah. So A times D transpose is a dot product is equal to 1 times 3 plus 2 times 4, right? In MATLAB, yeah. But if you say A dot star B is equal to 1 times is equal to 1 times 3 and 2 times 4, understand? Right? This point-wise multiplication is still a vector, understand? Okay? So this is point-wise multiplication, right? And to do a convolution is just one statement in MATLAB, understand? Okay? And it's a lot faster because FFT is a fast computation of EFT, right? Remember? Okay, so now it links, right? So now you understand why you need to study FFT. Now you understand why you need to study convolution because it allows you to tell you what's the output. Right? Okay? So that was linear convolution. So what we have done so far is linear convolution. And in linear convolution, the values in an array get shifted out. Right? You shift out. Right? You get shifted out like that. Okay? And this linear convolution, right? This is another example, right? When you have two rectangles and a linear convolution and the two sides the output becomes slanted, right? We saw that just now, right? No. Linear convolution can be done in the frequency domain much more effectively using FFT, right? Right? So I'm not going to go through this, it's too scary, right? So at the end of the lecture already. Right. But I'm going to give you some hits after. Listen, I just told you the result just now, right? The result is this box in yellow, right? And this is a derivation. We'll do that next time, right? But listen, we say we're going to use FFT to do the multiply and sum, very nice, right? Right? But there is one problem. Remember the problem that I told? There's one problem. What was the problem? What is the problem when you use FFT? Sorry? Periodic, very good. Periodic, right? So just now you do all these things, right? You know, do all this multiply and sum, right? Shifting, right? When you shift out, outside is 0, right? And then you multiply, it's all 0. When everything is 0, you get nothing, right? Right? When you use FFT, it's outside 0. Is it outside? It's outside 0. It's not 0, you know, the signal, even though it's like that. Even though the signal is like that, when it's outside, it repeats again, understand? And then when you slide, you're going to get some numbers here, right? Right? So when you use FFT to implement your convolution, you have to be very, very, very careful. You're dealing with periodicity count. Understand? Okay? So that one, we'll do it next time. There are ways to bypass this problem and still using FFT, understand? Right? The simple way, I mean, give you some heads up first. The simple way is to add zeros, right? Instead of saying my signal is like that, right? And tell FFT my signal is like that, right? Right? And then FFT will assume that it will repeat again, right? Right? What I'll do is, instead of telling the signal is like that, I'll tell FFT my signal is like that, 0. Okay? Right? So it will repeat much later, right? So later on when I do the shifting, it won't affect. Understand? So it's something called paired with 0. Alright? So when you do use FFT to do implement a convolution, you have to take note of this. This practical stuff, right? Okay? Now, I think I'll stop here. I don't want to go through this set of slides. And once again, those who are celebrating for your new year, happy new year to you. The rest, happy holidays. Okay?